Okay, so we just finished in the last class, chapter number 4, which is perhaps the longest chapter, the largest chapter in this semester in Engineering 17 course. And it did give you a bunch of different tool sets. Okay, now you're not only going to use the tool set and um, the reporter of all the tools. In this chapter, you're going to put them to good use. You're going to analyze a new terminal, a new device called operational amplifier. Okay, well, I'm going to begin with the end in mind. Okay, the normal idea is to go through each of these concepts and then at the end summarize. But today, for this chapter, particularly for the operational amplifier chapter, I'm going to begin with the end in mind. Or in other words, I'm simply going to give you a big picture summary of what OpAmp is all about. Okay, I'll pretend like we already completed the chapter and summarize the key takeaways and then go on to the analysis. Okay, and why would I want to do that? In the hopes that I don't overwhelm you with analysis. Okay, if I present to you the key points, and they somehow stick in your head, the analysis only seems to be an addition rather than a sore spot or a confusion point. Okay, so this is an interesting chapter. Some students might find this a little muddy or not so comfortable. So we're going to try something different. We are going to begin by summarizing first. Okay. Summary of operational amplifiers. What is an OpAmp? Okay, OpAmp is a 3-terminal device. It has more than 3 terminals, but the terminals of interest to me, there are three terminals. Okay, it's a 3-terminal device. Okay, it's a 3-terminal device with a negative input terminal, a positive input terminal, and an output. Okay, here is an operational amplifier. We have not seen an op-amp before. We only saw resistance, capacitance, inductance, voltage source, current source. Okay, a new kind of a device. It's an operational amplifier. It has 2 inputs. It has a negative input terminal and it has a positive input terminal. Okay, and then of course output, the output. Okay, it's a 3-terminal device. Let me write that out here. 3. It's a 3-terminal device. Okay, what else? 2 of these terminals are input. So this guy connected to the negative terminal, okay, is called the negative input, V in minus. Okay, and there's a second input terminal called the V in positive. Okay, so the main terminals of interest to us are the 2 inputs and 1 output terminal. In addition to that, the op-amp does have positive power supply and negative power supply. Okay, it does have positive and negative power supply. Well, how does an op-amp work? Simply, what it does is the relationship. What was the relationship between resistance and its current? V was I times R, right? The relationship between the voltage in a resistance and the voltage current in a resistance. Okay. Similarly, what is the relationship between the output voltage and the input voltages here on the op-amp? What the op-amp does is, okay, it takes the input voltages, the two terminals, okay? There are two terminals, right? The input negative terminal and the input positive terminal. It calculates the difference between those two voltages. So for example, this guy is 10, this guy is 5. So this term, or let me make this 3 just so I see the numbers clearly. 10 minus 3, which is 7, okay? 7 is the difference between these two terminals, okay? Now what the op-amp does is it amplifies the difference to form an output, okay? So where A is the gain. So if gain was, I don't know, 1000, okay? The V output would be 7000. Why is it 7000? The difference between the input and the output terminals is 10 minus 3, which is 7 volts. Okay, so let's say I apply 10 volts on the positive terminal and 3 volts on the negative terminal. That difference is amplified by a factor of 1000. So the output is 1000. Hence the name operational amplifier, OpAmp, because it simply amplifies. It amplifies the difference between the two input terminals. Okay, very simple idea. Okay, usually the value of A is really large. A is a big number most often times. Okay, let's see if I can. Okay, usually A is a very large quantity. Typically in the order of 10 kilo. Okay, 10 kilo. It's called open loop gain. It's close to okay, so that's the idea. Now let's see, let's play a hypothetical here. Questions so far, please. It's a simple idea. What an op-amp does is simply looks at the difference between the input terminals and then amplifies them. Okay, so I'll give you an idea. Let's say this number is 5, this number is 1, and the gain value is 10 to the 4. Okay, and this number is, let's make this number really 5 millivolts, 0.5 millivolts. Okay, since we're randomly picking these numbers, let's just do 0.1 millivolts. What would be the output in this case? What would be the output?
Would it be 4 volts?
4 volts. It's 0.6 millivolts or 5 volts rather. 0.6 millivolts. I'm sorry, I changed this number on you from 0.5 to 0.6. Okay, 0.5 millivolts times 10 to the 4, which is 5 millivolts. Sorry, 5 volts. Okay, so 5 volts. Now, and let's do one more case where this value is 0.8 millivolts. This value is 0.2 millivolts. In this case, the difference is 0.6 millivolts. Multiply that by the gain, you get a value of 6 volts. Okay, so the output, V output, in this case is going to be 6 volts because the difference multiplied by the gain factor. Okay, so this applies only within the limits of positive power supply and negative power supply. Okay, and I'll talk about that later. I'll show you why that is the case later. But for now, you know how to do the math. Okay, you take the difference between the positive and negative terminals, okay, and multiply that by the gain. Okay, so let's look at some more properties. Okay, of the operational amplifiers. Ideal OpAmp assumptions. Okay, in order to understand the ideal OpAmp assumptions, let's revisit the example that we looked at. Okay, let's revisit the example that we saw earlier. Okay, right here. Okay, now I'm going to give you some numbers that can make you think. So let's say the power supply is really, I don't know, plus 10 volts to the positive, okay, negative 10 volts on the lower side. Okay, and with these values, let's try to put some numbers on here. Let's go back to our 0.1 millivolts and 0.6 millivolts on each of these terminals. So V output is going to be 0.6 minus 0.1 millivolts times 10 to the 4, which is 5 volts. Okay, 5 volts. Now, I'll give you another number. Let's see, let me pick a different color here. Let me pick this guy. Let's say I apply a value of 0.1 millivolts and 0.05 millivolts. Okay, when I do that, let me pick some different numbers. Okay, 0.9 millivolts and 0.3 millivolts. When I plug these numbers, in this case, V output is going to be 0.9 minus 0.3 millivolts into the gain, which is going to be 6 volts, right? So far, so good. Let's see what happens if I pick a different value. If I pick a value that's more like so. Okay, let's see. I'm going to rearrange these here. Okay, now I'm going to pick a different value. Let's see what happens if I pick a value of, I don't know, 0 point. No, why 0 point? I'll pick a value of 3 volts over here. And I'll pick a value of 1 volt over here. Okay, what do you think happens to the output? What would be the value on the output?
Is there a sort of like a cap on the output, or like a?
Yes, exactly. If there is no cap, you would expect this to be 3 volts minus 1 volt times 10 to the 4, which seems to be 20,000 volts. A really, really large number. And that kind of is not practical. This op-amp cannot give you a voltage of 20,000 volts. There is a cap. And where do you think the cap would be? Where is a logical limit for this guy?
Is it the difference between the positive power supply and the negative power supply?
Very close, very close. It will be the positive power supply on the top side. You see what I mean? So think of, I'll give you an analogy when we do the next problem. Okay, let me give you a different number here. I'll give you a 4th number. Let's see, I give you a value of 2 volts over here and 5 volts over here. Okay, what would be the output in this case? V output equals to 2 minus 5 times 10 to the 4, which is going to be negative 30,000 volts. So the op-amp cannot provide so much of output because it is capped at the lower power supply, negative 10 volts. Okay, so the idea is there is a limit, a cap to the maximum amount of voltage that the op-amp can provide on the output. Okay, so in other words, we give you, let me add a page here. So really, V output max, the maximum value possible for V output is the power supply. So the output voltage is capped on the positive side to the VCC. V output minimum, okay, let me not write this as a negative, just so it's clear. V output maximum, V output minimum is capped to the negative VCC. Okay, I'll give you, like I mentioned, I'll give you an analogy. Imagine you are jumping on a trampoline inside your house. Okay, you may be able to jump hard, you may be able to take a very strong jump on it, but the highest that you can reach is only all the way up to the ceiling, right? So there's a ceiling. The maximum voltage that an op-amp can supply on the output. Okay. Similarly, how low can you go when you're jumping up and down in an on a trampoline inside a house? That's set by the floor of your house, right? So in other words, the maximum and the minimum height that you can reach when you're jumping up and down in a house is set by the ceiling, and the minimum is set by the floor. Similarly, When you're talking about an op-amp, the maximum and minimum output voltage is set by the positive power supply and the negative power supply. Okay? That's an op-amp. What's an op-amp? It simply is a three-terminal device which amplifies the difference between two of its input terminals. Does that make sense?
Yes.
Okay. So this is about the ceiling. Okay. Now I'm going to talk about op-amp ideal characteristics, ideal op-amp assumptions. Okay. Okay. When it comes to ideal op-amp, let me copy this. Okay, when it comes to an ideal op-amp, there are two assumptions that are important to us. The first one is it's an ideal assumption. It does not hold true in reality. Okay, the loop gain, you remember the open loop gain, the gain. Remember, I picked a large value for it, 10 to the 4. I picked a value of 10 to the 4. So the assumption is in an ideal op-amp, the loop gain, the open loop gain is infinite. This is not true in practical case, but to solve our problems in an ideal scenario, we assume that the open loop the gain is infinity. Okay, so the idea from here is, let's say there is some value plus 5 volts on the output. Okay, if plus 5 volts is on the output, remember V output is A times V input plus minus V input minus, right? So A is V output over V input plus minus V input minus. Okay, now the assumption was that this guy A, okay, the assumption was that this guy A is infinity and this is a small number 5. What does it tell you about the denominator?
That it's very small.
It's very, very small. It's 0, right? For this to be infinity, the denominator has to really be a 0 value. Okay, so that's the ideal op-amp assumption based on the idea that the gain is infinity. If the gain is infinity, then the difference between the two terminals is really, really, really small, so much so that they're virtually the same. Okay, so this is called virtual short. Okay, so this is the idea of virtual short. Okay, so a direct consequence of the assumption that the gain is infinity or really, really, really large is that the V input plus will ideally be equal to V input minus. Okay, that's the first op-amp assumption. The second op-amp assumption is that the amount of current going in, okay, to this into this device, oops, the amount of current going into this device, this guy, is 0. I in going into the negative terminal and I in going into the positive terminal, the assumption is that values, there's no current going into the, okay? The amount of current going in to the op amp is 0. So there's a name, we like to call it as infinite input resistance. Meaning the I input plus the amount of current going into the positive terminal of an op amp and the amount of current going into the negative terminal of an op amp are 0. Okay, so these are two conditions that we like to call as ideal op-amp assumptions. Okay, these are not true in a practical case, but we assume them anyways because they're going to make our analysis part really easy. Okay. The idea of virtual short. Okay, and then the idea of infinite input resistance. These are the two op-amp assumptions that we will use over and over and over again. Questions so far, please? Okay, let's continue our discussion on the op-amp. Right. Let's continue our discussion of the op-amp like so. Let me start by copying this. And then so we are looking at the summary of op-amp here, right? Summary of op-amps. The first idea is that the op-amp, let me see if I can. Okay. The first idea is that the output is an amplified version of the difference between the inputs. Okay. The second idea is that there is a maximum and minimum limit cap possible for the output. Okay. And the third idea is that there is a virtual short. Okay. And then there's also infinite input resistance. Okay. So these are the big conclusions for my op-amp scenario. Okay. These are my big conclusions for the op-amp. Okay. So let's continue our discussion of the okay. Let's continue our discussion of the op-amp here. If you were to plot this, if you were to plot the output of an op-amp as a function of the input, okay, if you were to plot the output of the op-amp as a function of the input, let's see. Okay, on the x-axis, you're going to, on the x-axis, you're going to plot the difference being plus minus V in minus. Okay, V in plus, the difference between the two terminals. And on the y-axis, you're going to plot the V out. Okay, as we saw earlier, the OpAmp value is responsive. The OpAmp is responsive, okay, up until a particular region, and then it begins to cap, okay? It begins to cap. So the idea that, so the maximum value of the output on the positive side is set by plus VCC, okay? The minimum value for the output is set by the negative VCC, okay? This is exactly what we saw in this equation, just shown in a figure, okay? So the maximum value of the output is set by plus VCC, where it begins to cap, and then the minimum value is called the minimum value is set by the negative power supply. Okay, so we like to call them, we like to name these regions. Okay, let's see. This region, we call it as positive saturation region. Okay, the region where the output is capped by the positive power supply is called the positive saturation region. This region is called the negative saturation region. So any region to the right is called positive saturation. Okay, any region to the left where the output is capped is called the negative saturation. Okay, and then this guy, okay, this region in between, okay, these 2 points, this is called the linear operation region. Okay, that's called the linear region. Okay, this is where your OpAmp can amplify. Okay, where the output is a slant line, it's not saturated. Obviously, saturation is a bad thing. Then the output is independent of the input. Even when the input is changing, the output does not change. Output is stuck, right? So there's a saturation on the positive side, there's a saturation on the negative side, and then there is a linear region of operation. And we always want to operate in the linear region. Okay, that's this guy. It's the linear region of operation. Questions, please. Questions so far?
Everything looks really good.
The slope of the line, that would be the gain.
Yes, thank you. Thank you. The slope of this line would be gain. I didn't want to mention that out of the fear that I might be throwing too much information at you, but let's see. The slope of this guy, okay, that would be the gain. Okay, the gain would be the slope of this guy. If the gain is high, then your straight line would be more steep. Okay, if the gain is really low, then your line is going to be more slant. Okay, something like that. But the slope of this guy is the gain. Other questions, please. Okay, let's see. So this is summary of OpAmp, page 3, right? Summary of OpAmps. It's a 3-terminal device. The output is max, and then OpAmp assumptions. summary of OpAmps continued. So let me write it here. Okay, so we are summarizing OpAmp without going into the actual analysis. I'm just giving you the different different behavior traits of an OpAmp. Okay, so now I'm going to give you another a couple more applications of OpAmp, a few applications of OpAmp actually. Okay, summary. Summary of OpAmp, continue. Let's see if we can look at the different connections for the OpAmp. I'm going to still copy this guy. Okay, and paste it here. Okay, now what I'm going to do is to just simplify the diagram by not showing the power supplies. I don't want to show the power supplies anymore, simply because it's cumbersome to draw them all the time. Okay, it's not that there's no power supply. We definitely need power supply to operate op-amps. We just don't show them explicitly. They are understood implicitly. Okay, so the same thing with gain as well. I sometimes show the gain, but sometimes I understand that it is there. Okay, now I'm going to show you what is called an inverting amplifier. Okay, let me write it over here, inverting amplifier. Okay, inverting amplifier configuration is there is a resistance connected over here, and I like to call this as RS. Okay, and then the output is tied back to the input through another resistance. Okay, let's call this as RF for feedback resistance. Okay, for feedback resistance, RF. Okay, feedback resistance, RF. I'm going to tie one of these positive input terminals to ground. Okay, this is called the positive input terminal is tied to the ground, and I apply a source, a voltage source to the input, negative input terminal here. Okay, so plus, minus, Vs. Okay, see what I'm doing? I have taken my op-amp. Okay, I took the op-amp and then I tied it in a feedback configuration, meaning the output is tied back to the negative input. Okay, negative terminal of the op-amp through RF feedback resistance. And I'm applying an input signal to the negative terminal. So in this case, what happens is I'll give you the expression here and then worry about deriving that at a later time. Okay, so V output is going to be the input Vs multiplied by some number, some factor of RF and RS. Okay, so inverting amplifier, INVER, inverting amplifier. Okay, the idea of inverting amplifier is that the output, okay, the output V output okay, is an amplified version of the input. Okay, it's an amplified version of the input. It's an input Vs, okay, multiplied by some gain where the gain is negative. Do you see what I mean? So it's called inverting amplifier for two reasons. Okay, the input signal Vs is applied to the negative terminal here. Okay, that's the reason why the overall output is negative RF over RS. Okay, so I'll give you a cousin sister of this. Okay, I'll give you a cousin sister of this, which is a non-inverting amplifier. Let me give you a non-inverting amplifier just so you see the difference. And by looking at the difference, you'll understand both of them better. Dang it. There you go. Okay, so I'm going to present to you a non-inverting amplifier in this case. What is a non-inverting amplifier? It's very similar. Okay, what I do is I still tie a feedback, okay, to the negative terminal. Okay, the output is still tied back to the input. Okay, through a feedback resistance RF. Okay, there's a feedback connected to the negative terminal here. In addition, there is a resistance RS over here. Okay, RS, which is now tied to ground. Okay, on the positive side, on the positive input, instead of tying this to a ground, I don't do that. What I do is to apply a signal to the positive input. Okay, so the Vs that was earlier applied to the negative terminal is now applied to the positive terminal. Okay, does that make sense? And I'm not going to show the power supplies explicitly. I'll just, imply them. Okay, the main difference between the inverting and non-inverting configuration is that the positive supply or the signal, okay, the input signal, if it is tied to the negative terminal, then we call it an inverting amplifier. If it is input signal is tied to the positive terminal, then we call it a non-inverting amplifier. Okay, a non-inverting amplifier. Let's see. Okay, non-inverting amplifier. Let me try to give you the value for the output here. Okay, a non-inverting amplifier. For a non-inverting amplifier, the output is the input multiplied by some gain. Okay, the output is the input multiplied by some gain. Okay, if you compare these two, let's see, if you compare these two results, okay, this guy. Okay, and this guy. If you compare those two results, one of them is positive because 1 plus RF RS, 1 plus RF over RS, that term is positive over here. And then on the top, the term, the multiplying factor, negative RF over RS, that's negative. Okay, so in the non-inverting amplifier, the gain is positive, and in the inverting amplifier, the gain is negative. Does that make sense?
Yes.
Okay, the main difference between how these op-amps are configured, how these op-amps are connected on their terminals is that an inverting amplifier has an input signal going to the negative terminal, while a non-inverting amplifier has an input signal going to the positive terminal. That's all there is to it. Okay, questions, please.
Professor, I have a question.
Yes.
The equations for V out, are those derived using like a KCL?
Yes, yes. These are derived. I'm going to walk you through the derivation of these. These are derived using the ideal op-amp assumptions.
Okay.
Remember, we made two assumptions, that the V input plus equals to V input negative, and then that the input resistance is infinity. Now combine those with KCL, you'll get these results. That's a very good question. It tells me that you are thinking a few steps ahead of the class, which is a good thing. Okay. And I'm going to show you the analysis on how to arrive at these results. But before that, I just wanted to give you the results, just so you're not muddled or confused through the con maze of equations. Okay. Other questions, please. Okay. Let's see. We are looking at, we are summarizing the behavior and the characteristics of an op-amp and also the applications of an op-amp. So far, we looked at two of these amplifier configurations, right? A non-inverting amplifier and an inverting amplifier. Let's see if we can take this a little further. Okay. Summary of OpAmp continued. Let me. Okay. Let me see if I can give you more circuits that represent the OpAmp. Okay. Here, I'm going to use something similar to this guy. Okay. Let's see if I can move this guy away a little bit. And duplicate this. And one more time. Okay. Now what I'm going to do is to tie all of these together and apply the combined, okay, value right here. Okay. So what I'm doing is in effect applying not one input signal, but 3 input signals. Okay, I'm applying 3 input signals here. Okay, let's see if I can rearrange this a little bit more. Okay, 3 signals together applied to input signal. What do you think the result would be in this case? So this is still a modification. This is still a slight modification of the inverting configuration. Okay, so what I'm going to do is I'm going to change these numbers to RA, RB, and RC. Okay, I'm going to call this as RA. I'm going to call this as RB. I'm going to call this resistance as RC. Okay, this voltage, I'm going to call it as VA. I'm going to call this guy, the one in the middle, as VB, and the one down below to be VC. Okay, earlier, when you had only one voltage source, you had V output. Okay, V output was V input or V source times negative RF over RS. Okay, where this was your VS, and this was your RS. All right. Now, instead of one signal, I have 3 signals here. So the output is still going to be very, very same, very, very similar. Okay, it's going to be same, very similar. V output is going to be the VA multiplied by the same factor, RF over RA, plus VB multiplied by some factor, negative RF over RB, plus VC, that is multiplied by negative RF over RC. Make sense? So this is called, you should not be surprised to know that this is called a weighted summing amplifier. Okay, it's called a weighted. This is called a weighted summing amplifier. It's easy to see why it's called a weighted summing amplifier. I'll show that to you in just 1 second. Okay, look at the input. The VA, the input that is applied here, is showing up here, multiplied by some gain weight, followed by this guy, VB. One of the inputs that is applied over there is showing up over here, that is added to the output, followed by this guy, followed by, I don't know, let's see. Okay, that guy showing up over here. Okay, so there are 3 inputs. Each of those inputs are showing up in the output as being added. Okay, they're added. The 3 inputs are being added. And how are they added? They're not simply added, they're added by some kind of weight. Okay, there is some weight over here. Okay, each of the inputs are multiplied by some gain factor and then added, hence the name weighted summing amplifier. So the output is VA times some gain plus VB times some gain plus VC times some gain. But don't forget that this is inverting. Configuration. Remember, this is inverting configuration because the inputs are all applied to the negative terminal. I'll give you, you can think of it that the three inputs here are being added at that node. Okay, so the three inputs are being added at that common node. Okay, and then the overall input, which is the sum of the three, is being magnified by their particular weights. Does that make sense?
Yes.
We have taken a simple amplifier, a simple operational amplifier, and then multiplied, okay, and implemented a weighted summing configuration. Okay, questions, please. Okay, so let me see if I can present just one more. Never mind. We'll not worry about that application. Difference amplifier. When you apply some input at the positive terminal and also at the negative terminal, what happens? Well, I'll present that later. Okay. For now, let's quickly review what we did so far, and then we'll go on to the analysis here. Okay. So we started looking at the operational amplifiers, a brand new device. Okay, it's a 3-terminal device. Okay, its basic characteristic is that it takes two power supplies, a positive power supply and negative power supply, and it has two input signal terminals, V input negative and V input positive. Okay, now the output is an amplified version of V input plus minus V input minus. Okay, typically the open loop gain, A is called the open loop gain, is a really large number. Okay, and then we looked at some examples. I showed you some examples, plugging in different numbers. What happens when these values are different numbers? Okay, so you know the output. One important characteristic is that the output maximum or the ceiling is set by the VCC, and the output minimum or the floor is set by negative VCC. Okay, that's where the OpAmp begins to saturate. Okay, so even if the input changes at that point of time over that number, the output does not change. The output is capped or limited to the maximum or minimum power supply. Okay, so V output maximum possible is plus VCC, V output minimum possible is negative VCC. Okay, that's for an OpAmp. Okay, and then we went on to talking about ideal OpAmp assumptions. Okay, two OpAmp assumptions, and we'll come back to using them over and over again. The first one is called the idea of a virtual short. Okay, which dictates that the voltage at the positive terminal is exactly the same as the voltage at the negative terminal. Okay, and this is owing to the fact that the open loop gain is a really large number. Okay, the first rule is the voltage that you apply on the positive terminal will automatically show up magically on the negative terminal. That's the first ideal OpAmp assumption, called a virtual short. The second one is that the input resistance looking into the OpAmp is infinity, meaning that the current going into the OpAmp really is zero. I input negative and I input positive is really 0. Okay, that's an ideal OpAmp assumption. Okay, then we started looking at the graphical representation of the maximum and minimum limit for V output possible. Okay, this is V output maximum. V output max is plus VCC. V output minimum is negative VCC. Okay, that information is shown using a graph, and then the gain is shown to be the slope here. Okay, so that's the idea. Now we went on to discussing different configurations. Okay, what happens when you apply an input to the negative terminal and tie the output back into the negative terminal? Okay, then we have what is known as an amplifier, an inverting amplifier. The output V out is a magnified and inverted version of the input. Okay, Vs times negative RF over Rs. That's V out. Okay, if you change this configuration slightly, and instead of applying the signal to the negative terminal, what happens if you apply the input signal to the positive terminal? In this case, the output is going to be Vs multiplied by some positive number, okay, or amplified by the positive terminal. The V source is applied to the positive terminal over here. Okay, then we looked at what is called a summing amplifier. Okay, summing amplifier. Instead of having just this guy, okay, instead of having just one input applied to the negative terminal, what happens when I apply more than one inputs? Okay, then the exact same idea of an inverting amplifier, except that 3 inputs.
Hi, I can't hear anything.